All right, I'm going to go through some in-class problems on internal forces. So this is the first one, and they're asking us to determine the internal forces at a point 25 feet from the left of the beam. So the first thing we have to do is find the reactions. So this is a pin, so we'll have an AY and an AX here and a BY at the roller. And we can use the moment about A to find BY, and then some of the forces in the Y direction to get AY. So in the interest of time, this is 900 pounds and this is 600 pounds, and AX is 0. So if we're going to cut this 25 feet from the left side of the beam, it's going to be cut somewhere about here. And I can draw that free body diagram. So we have 900 pounds, 0 if we want, and then we have a force coming down of 500 pounds. That's 20 feet from this edge, and then there's another 5 feet. And essentially, you can think of this as like a fixed point. And so, at a fixed support, because it can't move relative to the other side of the beam, so you kind of think of it as fixed, you're going to have a normal force, a shear force, and a bending moment. And so then we just use the sum of the equation, the sum of the forces, or the sum of the moments about a point, to find each of these. So if I do the sum of the forces in the x direction is equal to 0, the only thing that we have in the x direction is n, so that is 0. Then I can do the sum of the forces in the y direction is equal to 0, and I have 900 going up minus 500 minus v. And so v turns out to be 400 pounds. Okay, and it is pointing down, but that is the convention for positive shear. So this is a positive 400. And then I can take the sum of the moments about that point there, and we have, let's see, the 900 is going to go counterclockwise, or clockwise, sorry, so it'll be 900 times 25 plus 500 times 5, and then plus mx, I guess. And so if we do that out, let's see, we get 500 times 5 is 25. And so if I take mx to the other side, whatever that is 20,000 foot-pounds. Okay, and I made this positive because it is going counterclockwise. Now, just to show you, and it is positive because that's the way that our convention is. But I could, if I had wanted to, taken the right side of the beam, and then we have the 600 pounds here. We have 1,000 pounds there at 50 feet. And then at, well, then this would just be 25 feet. Right? And so then I would have my normal force, my shear force, and my moment. And so again, I can take the sum of the forces in the x direction is equal to 0, and so m is equal to 0. The sum of the forces in the y direction is equal to 0, and I have 600 minus 1,000, 600 minus 1,000 plus v. And so v turns out to be 400 pounds. So notice that when I do the right side of the beam, my v is pointing up. When I do the left side, the v is pointing down, the shear force is pointing down. But in both cases, I get a positive shear. Right? So this is why it's important that you use the convention, because if you just told me here, you could have told me that was negative, right? Because of the way it's pointing, and it's not. It's a positive shear. So you have to use that nomenclature. All right, and then the same thing for the moment. So if I take the moment about this point, let's see, my 600 is counterclockwise, so that's going to be 600 times 75 minus 1,000 times 25, and then my m is going clockwise, so it is actually going to be negative in my equation, and that all equals 0. And if you multiply that out, you will get 20,000 foot-pounds. So you get the same thing. Okay, but notice that in this equation, even though mx is, the convention is that it's positive, when I take the moment about this point, because it is going counterclockwise, I put that in as a negative moment. All right, and then we could also do it 25 from the right side of the beam, but I want to show you another example. So in this example, we have, again, they're asking us, let's see, determine the internal normal force, shear force, and moment at point C, which is located just to the right of this couple moment. So it's going to be, the couple moment's going to be applied on the left side of the beam. All right, so again, I have AY, AX, and then I have this normal force at B. All right, and B turns out, if I take them, find the reactions, this is 3,608. My AX is 1,804 pounds, and AY is 2,875 pounds. Okay, so this time we will have something in the normal. Okay, so if I break it, and we'll take the left side of the beam. All right, so I have my 1,804, I have my AY 2,875. Okay, then I have the distributed load. Well, it's 500 pounds per foot, but on the left side of the beam, it's only working over the 6 feet. So I take the 500 pounds per foot and multiply it by 6 feet. And so that's going to give me 3,000 pounds. And since it's a rectangle, this is going to be 3 feet and 3 feet. Okay, then I will have this moment, because the C is located just to the right of that moment. So I'm going to apply my couple moment, which is 15,000 pound-feet. And then at C, I will have my normal force, my shear force, and my moment. So we can call these NC, NC, and C. So now, if I do the sum of the forces in the x direction is equal to 0, I get 1,804 plus NC is equal to 0. And so NC is negative 1,804 pounds. Okay, so I know that NC is actually going the opposite direction. And because I drew them all positive, so this is why I always draw them in the positive, that if it comes out negative, then I know that it's a negative normal force, and I'm good, right? Because this is positive on the left side of the beam, but if I go this way, it's going to be negative. So I don't have to worry about the signs if I always draw them in the positive direction. So then we have the sum of the forces in the y direction is equal to 0, and we have, 2,875 minus the 3,000 minus VC, right? And so VC turns out to be 125, sorry. And let's see, it's actually turns out to be negative 125, right? And so I know, whoops, pounds. So again, I know that my shear force is actually going up, but it is considered negative. If I did the opposite side, it would be going down. And then last, I'm going to take the moment about, this cut, or C. And so the 1,805 doesn't act at that. I'll have the 2,875 times 6. And that's going to be negative because we make it counterclockwise positive. Then we have the 3,000 times 3, and that will be positive. And then we have this 15,000. It's an applied moment. It is clockwise, so that will be negative. It's no distance because it's already a moment. And then we have the MC, and that all equals 0. right? And so if I calculate that out, I get MC is equal to 9750 foot-pounds. And because it turns out positive, I know that I've drawn that in the that it's going to be bending concave up. Okay, and similarly, like I said, if I wanted to, I could have taken the right side of this beam, and we have this here, which is the 3608, and then similarly I'd have the 3000 at 3 feet and 3 feet, and we'd have the shear force, the normal force at C, we'd have the shear force at C, and we'd have the moment at C. And so if I break this into its components, let's see, this is going to be, what, 30 degrees here, so we'll have 3608 times cosine of 30. So let's see, this will be going up here 3125, and 3608 times the sine of 30 will be 1804. Okay, so if I take the sum of the forces in the x direction, I'll have negative equals negative 1804 minus NC, and so NC is negative 1804, so I know again that it goes in the opposite direction here, but it's a negative shear. The sum of the forces in the y direction is equal to 0, so I have VC minus 3000 plus 3125, and so VC ends up negative 125. So again, the opposite direction. And then here's the difference. When I take the moment about that point C, right, I have negative MC because of the way that it is going counterclockwise, plus the 3000 times 3 and then plus. Okay. Whoops, I went the wrong way. I was going around that instead of this. So this one is also negative, and then this one is plus 3125 times 6. Okay, and if you calculate that out, MC turns out to be 9750 foot-pounds, and again, it is going, tending to bend this thing concave up. Okay, so one last problem here. It's asking us to find the normal shear force and moment at point C. So again, the first step is to find our reactions. There's a roller at A, so that's going to be AY, and at B is going to be a BY and a BX. Using the whole thing, take the moment about B, find AY, sum of the forces in the Y direction to find BY, sum of the forces in the X direction to find BX. So this will be 0, BY is 6 kilonewtons, and AY is, actually I don't know that I found AY, so I guess we'll do that right now. So let's see. If we take 6 times 6 divided by 2, that's my whole force. So that's 36 divided by 2, that's 18. And so the sum of the forces in the y direction would be negative 18 plus 6 plus AY, and so AY would be 12. So this is 12 kilonewtons. Okay, so then we can break this apart, and we could either do A to C, or we could do C to B. And if we do A to C, we have a force like this, and if we do C to B, we have a force like that. So this one, again, it doesn't matter which one you do. We'd have the normal force, we'd have the shear force, and then we'd have the moment. normal C, normal C, and then VC and VC. But this side here is going to be a little bit easier because I don't have to break it up and find two different forces. So that's the side I'm going to choose, which is why I guess I'd only found the By to begin with. And so what I need to do is find the height of this. So I'm going to take the slope of that. So we have 6 over 9. That gives me the slope, and then I will multiply that by 3. Oops, 6 over 6. Sorry. Because this is 3 plus 3, sorry. And then multiplied by 3. So we'll get 3 should be the height right here. So that should be 3 kilonewtons per meter. And so if I take that as 3 times 3 divided by 2, I'm going to get 4.5, right? 3 times 3 divided by 2 is 4.5. And that will be closer to the taller end. So this would be a distance of 1, and this would be a distance of 2. All right, and then I can take the sum of the forces in the x direction is equal to 0. Well, my Bx was 0, so I have 0 minus NC, and so NC turns out to be 0. All right, and then the sum of the forces in the y direction, I have negative 4.5 plus 6 plus VC based on the way that I drew it, and that all equals 0. And so VC is equal to negative 1.5 kilonewtons. And this is what you would report. Doesn't matter if we did it on the opposite side, right? We'd have, the VC would go the other direction, but you're going to report it with a negative because that's the convention. And then finally, if we take the moments about that cut, MC is negative based on the way it's drawn, minus 4.5 times 1, that's the distance, plus 6 times 3. And so if I do that out, I get MC is equal to 13.5 kilonewtons per meter. That all equals 0. And again, that would be positive because this turns out positive, so I know that it's bending it concave up.